These are notes for section 1.4, inverses of functions. So before we start this, I want to review a couple of definitions. So we'll start with a relation. And a relation is a set of ordered pairs. So one example of a relation could be the set 1, 1, 2, 2, 2, 3. And if you remember from earlier this year also, we said a function is a relation where every input pairs to exactly one output. So in the case here above, this is not a function because we have the input of 2 that pairs with 2 different outputs. So an example of something that is a function, well, I could have 1, 1, 2, 2, and then instead of having 2, 3, maybe I'd pick a different x that I haven't used already, like 3, 3. So what we want to do now is talk about an inverse. The inverse of a function or inverse of a relation is basically a map that takes the outputs back to the inputs. So let's say that I have the inputs here, or the domain, -4, 0, 1, 4, and the range, -2, -3, 2, 1, and my function f takes pairs -4 with -2, 0 to -3, 1 to 2, and 4 to 1. An inverse is going to go and do the opposite direction. So the inverse is going to take -2 back to -4, -3 back to 0, 2 back to 1, and 1 back to 4. And the notation we use to write an inverse is we write f to the -1. Now, just as a side note here, f to the -1 is not 1 over f. That's a rule for variables. For functions, a negative exponent simply means that it's an inverse. It does not mean that it's a reciprocal. So that's a property of like numbers and variables, not a property of functions. So don't get those notations confused and those definitions confused. Let's view now, instead of viewing an inverse through a mapping diagram, let's view an inverse as a set of ordered pairs. So if I have the function, and it's going to be the same function I've written above, right? -4 goes to -2, 0 goes to -3, 1 goes to 2, and then 4 goes to 1. The inverse for this function, well, it's going the reverse direction. So instead of writing the xy here, I'm going to write the yx. -2 is the input, and -4 is the output. So all I need to do to find the inverse is to swap the x's and the y's. Okay, well that's not so hard, right? Finding the inverse of a set of ordered pairs is quite easy. What if I have instead a graph? So I will 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4. If I graph f of x, so there's the point -4, -2. Again, this is the same f of x from before. 0, -3, 1, 2, 4, 1. And if I want to find the inverse of this, I can reflect this graph across the line, y equals x, which is essentially the same thing as swapping the x and y coordinates. So that is -2, -4. So that's, this one gets reflected to there. -3, 0. So this one is reflected to there. 2, 1. That one is reflected to there. And then 1, 4. This one is reflected to there. So with just points as my function, it's not terribly interesting doing this. Let's do another example of reflecting across the line y equals x. There's something that's a little bit more complicated. We'll take like a continuous graph, like a parabola. So here's my graph of f of x. To draw its inverse, I am going to draw on the line y equals x. So again, this is just a point where, or the set of points 1, 1, 2, 2, 3, 3, etc. So again, where the x and y's are the same. That's how I plotted that. I just kind of eyeballed it because it divides the first and third quadrants and like equal parts there. But if you wanted to get really specific, that's how I graphed it. Now to draw this, I'm going to start by drawing this part of it. So flipping that over, I get that. And I'll draw this part. So flipping that across the line, I get something like that. And now I'll draw this part, where folding it across the line, I get something like that. Now take a moment and look at this for a second. I notice here that f of x, this is a function. But if I look at its inverse, this is not a function. Again, I knew f of x was a function because it passes a vertical line test. There's no vertical line I can draw that intersects that function more than once. But that's certainly not the case for f inverse, right? There's lots of places where I can draw a vertical line that intersects that graph more than one time. So why exactly is that happening? Well, if you remember, we said that an inverse we basically can find by swapping the x and y coordinates. So, what I can say is, if my function f of x, we'll go back up and look at this for a moment, has 2 points, say this point -2, 4, and this point +2, 4. Notice those have the same y coordinates. When I make their inverse, they have the same x coordinates, right? We have 4 +2 and 4 -2, and they're going to fail a vertical line test. So whenever this occurs, where I have repeating y coordinates, I know that I'm going to have an inverse that is no longer a function. So let's give this a definition. This has a special name. That definition is called, or that name is called one-to-one. We say a function is one-to-one if two y coordinates are the same, then the two x coordinates also must be the same. Okay. Or, probably more intuitively, a function is one-to-one if it passes a horizontal line test. And this is probably the more practical definition for us. This is the one that we use in practice. So to tell if something passes a horizontal line test, well, I can just look at the function. So let's say we're talking about this as my function f of x. I can see that this function f of x definitely does not pass a horizontal line test. So we can say that f inverse is not a function because f of x is not one-to-one. And that's a theorem. So I should probably say that formally. If f of x is 1 to 1, then f inverse is a function. And we can check that 1 to 1-ness just doing that horizontal line test, as I described above. Okay? So we've talked about how to find inverses if we describe our function as a mapping diagram, where we just reverse the arrows, as a set of ordered pairs, we swap the x and y's. As a graph, we reflect across the line y equals x. What we still need to talk about, there's not one other way that we represent functions, and that's with an equation. So to find the inverse of a function when it's written as an equation, what I'm going to do is it's a kind of a two-step process. Step one, we solve the function in terms of x. And step two, we swap the x and y variables. So let's do an example. Let's say that we have f of x equals 3x plus 4. Now remember that we use f of x and y interchangeably, so for just the sake of simplicity, I'm going to write this as y equals 3x plus 4 instead of f of x equals 3x plus 4. It doesn't really matter. Now I'm just going to solve for x the same way that I would in your algebra or pre-algebra class. So I'll begin by subtracting 4 from both sides. So y minus 4 I can't do anything to, so I'll just write as y minus 4. And then we'll divide both sides by 3. So I have y minus 4. I'll divide by 3. And now the x is by itself. So I've completed step 1. Step 2, I'm going to swap the x and y variables. So I have then x minus 4 equals 3. I'm sorry, x minus 4 over 3 equals y. Or I could write f inverse of x now equals x minus 4 over 3. Okay, well that's pretty straightforward. Not much to do there. Let's do one more example before we move on. Let's do one maybe with a fraction in it. So let's consider the function f of x equals x over x plus 1. So I'm going to start the same way. I'm going to start by writing f of x as y. And now I'm going to solve for x. The solving for x in this situation is quite a bit more complicated. First thing I'm going to do is get rid of the fraction. So this looks like a proportion. So just like in your geometry class, I'm going to start by cross multiplying. So that gives me x times 1 is equal to y times x plus 1. And it doesn't matter which one you write on which side. It's okay. You could have easily written y equals x plus 1 equals x times 1. No big deal. Now I'm going to multiply these things through, so that distributes, and x times 1 is just x. And now I'm going to get the x's all on one side. And I notice here, since I have x's in each term, they contain a common factor of x, so I can factor that x off. And now if I divide both sides by 1 minus y, the x is finally by itself. And I've completed now step 1. Whew, that took a little bit of work, but still not so bad. Now I'm on to step 2. Step 2, all I need to do is swap the x and y variables. And instead of writing this as y equals, I could write it as f inverse. So the inverse of f of x in this case is x over 1 minus x. Again, not so bad. One thing that I might be interested in is doing a modeling problem with an inverse. So what I'm going to reference here is our textbook. So if I pull up my textbook and I log in, I guess I probably could have figured this out beforehand, but oh well. Unit 1, Module 1, Lesson 4. Student edition. And I'm looking at example 2 on page 51 right now. Oops, there it is. It says for the given function, state the domain of the inverse function using set notation, then find an equation for the inverse function and graph it, interpret the meaning of the inverse function. Okay, so I'm going to start by finding the domain for the regular function. So the regular function says is C equals 3.5G gives the cost C in dollars as a function of the number of gallons gasoline G when the price is $3.50 per gallon. So the domain of this function is restricted. It's a real world problem. So clearly the domain for this function is really only positive numbers or non-negative numbers, right? I can't have negative gallons of gas, and really realistically, if I had a big enough car, I could have as many gallons of gas as I wanted to. So the domain is basically G is greater than or equal to 0. Now, since we're multiplying any G by 3.5, I can get any value for C, right? If I do 3.5 times the smallest G, 0, I get 0. And if I pick G as 1, C times 1 is 3.5, and I can get all the values between 0 and 3.5 by picking some numbers between 0 and 1. And really, I get that the domain for this inverse is also greater than or equal to 0. And then to find the inverse, I do what I did before. Is I just solve the equation in terms of G, so I divide both sides by 3.5, and then there's my inverse function. So not so difficult. And then I guess we graph it. So that's pretty straightforward, I think. And that ought to be enough for section 1.4. So that concludes section 1.4. Again, the major skill that we talked about was being able to find an inverse in these notes. We talked about how to find that inverse in a variety of different ways, whether your function was a mapping diagram where you just reverse the arrows, a set of ordered pairs where you swap the x and y's, a graph where you reflect across the line y equals x, or as an equation where you solve for x and then swap the x and y variables. And that's the idea. Okay, thanks guys. Bye-bye.